that is the bare one, which is abbreviated as BA or SS, which implies the bare without any modification. When the cleaned substrate is subjected for the NdYAG pulsed laser, it is Nd is neodymium, Y is yttrium, A is aluminum, G is garnet. So when it is subjected to the pulsed laser with an wavelength of 1064 nanometer with a pulse energy of 20 millijoule, it gets textured by means of honeycomb. Honeycomb texture has been drawn over the one side of the stainless steel. Then resulting substrate is abbreviated as SSLR. It is the expansion is single side laser rusted stainless steel. When it is irradiated on both sides, that is double side, it requires 6 minutes 32 seconds. Whereas for single side irradiation, you need 3 minutes 16 seconds. Whereas for double side irradiation, you need 6 minutes 32 seconds. So that resulting substrates are termed as DSLR, that is double side laser rusted stainless steel. So here we are using two kind of substrates. One is single side irradiated and another one is both side, double side irradiated substrates. These substrates are subjected to the surface analysis such as XRD, XPS, SIM, EDOX, 3D, and contact angle. And further, it is evaluated for its electrocatalytic behavior through electroanalytical techniques such as LSV, CV, and EIS in 1 molar KOH solution. This slide shows the SIM, 3D, and the contact angle of the bare, single side, and double side laser rusted stainless steel. Figure A is corresponding to the bare stainless steel, which consists of smooth surface with gray silver color. Whereas when the pre-cleaned stainless steel is irradiated on single side, the perfect honeycomb texture has been drawn over the substrate, and which is confirmed visually through the formation of light brown colored layer, that is, which is nothing but rust. That is, the main constituent present in the stainless steel is Fe, which undergoes the oxidation to its oxides. When the substrate is irradiated on both sides, the intensity of the brown color is increases. That is, dark brown rust layer is formed over the substrate, which confirmed that thick or dense rust layer or oxides of iron, nickel, and chromium is formed over the surface. Then D, E, F are the respective 3D images of the substrates. When we look this, the surface roughness is increasing from 0.2 to 12.1. So when we irradiated the metal surface by means of laser, the surface roughness will also increases. Simultaneously, the wettability is also increasing. We can see from figure G that it is respective for the bare stainless steel substrate whose contact angle is about 29 degree, whereas for single side it is about 2, whereas for double side it is about 1. So laser radiation is useful for the creating rough texture as well as for the super hydrophilic texture. Next one is EDS analysis. So the as fabricated laser textured material has been subjected for EDS analysis. From this graph, we can able to determine or identify that the concentration or percentage of oxygen is increasing, which is highlighted in the red box. So we can see from figure A, that is bare stainless steel has only 8% of oxygen, whereas single side and double side has nearly same, that is about 38%. So the oxygen percentage is increasing, which reveals that during laser radiation, oxidation takes place. Simultaneously, the concentration of chromium and nickel is decreasing, which shows that the atom present in the crystalline package in the bulk get redeposited over the over the surface, and which are undergoes oxidation to a multivalent oxides. The formation of these multivalent oxides are confirmed through the XRD and XPS analysis. Figure A is for the XRD analysis. We can see when compared to bare stainless steel, single side and double side laser rusted stainless steel possesses a new peak or XRD pattern around 44, which is respective to the ferrite. That is, ferrite means it is the magnetic behavior oxide of the steel, whereas bare consists of only austenite. Austenite means it is less magnetic behavior element. So when we irradiated the stainless steel by means of laser, the magnetic property will also change, which plays an important role in the water splitting. Further, the binding energy of the as formed oxides are confirmed through XPS analysis. From this spectrum, we can able to confirm that the percentage or the binding energies are shifted towards a higher energy region of oxygen, nickel, iron, as well as chromium. Table 1 represents the Fe2P 3x2 spectral fitting data. Here you can see the differences. Major difference is when compared to bare stainless steel, this laser textured stainless steel possesses higher oxidized ions, that is Fe3, that is Fe3 oxyhydroxide. More number of three valent ions are formed over the single as well as double rested stainless steel. Likewise, chromium, the chromium 6 oxide, higher valent oxide is formed only on the DSLR, that is double side laser rested stainless steel. Table 3 also shows that nickel 3 plus is predominantly formed in the case of double side laser rested stainless steel, which is further supported by means of OAS spectral fitting parameters. From XPS survey spectrum as well as the table, we confirmed that during laser radiation, high valence ion chromium and nickel oxides are formed over the surface. This is the cyclic voltammogram, which is recorded in the non-Faradaic region, because through this only, through non-Faradaic region only, we can able to determine the electrochemically active surface area, that is directly proportional to the double layer capacitance. So if double layer capacitance is high, means definitely electrochemically active surface area is also high. If electrochemically active surface area is high, means definitely it must possess high electrocatalytic activity. So figure A is for bare, figure B is for a single side, C is for the double side laser rusted stainless steel. From the graph itself, we can determine that figure A, the current density is about 0.036, whereas here it is moved towards the positive region, and also for double side, the current density is also increasing. This slide shows the OER, oxygen evolution reaction of the as fabricated electrodes. Figure A is the linear sweep voltammetry curves of bare, single side and double side laser rusted stainless steel. So it's a one kind of fuel cell reaction, as Dr. Gaudaman said in the earlier presentation. So it's a one kind of fuel cell reaction. The fuel cell reaction output, minimum output is about 10 milliampere. So all the three electrodes achieved that. But among these three, the double side laser rusted stainless steel achieved very low over potential of about 382 millivolt. So using this and extrapolated on the kinetically controlled region, we can able to determine the taffel slope, which is depicted in figure B. Again, among these three, the double side laser rusted stainless steel exhibits low taffel slope of about 52 millivolt per decade. Here, the potential scales are converted into RHE scale, that is reversible hydrogen electrode scale. Why means? Because all other references electrode are pH dependent, while the reversible electrode is of independent of pH. That's why we are expressing in terms of RHE scale. Figure C is for the calculation of double layer capacitance using the following equation. CDL equal to JDL divided by nu, that is current density divided by the scan rate. Here also we achieved the same trend, that is double side laser arrested stainless steel exhibits a higher double layer capacitance of about 351 microfarad per centimeter square. Using this double layer capacitance, we can able to determine the roughness theoretically using the formula RF equal to CDL divided by CDL dot, which is nothing but the smooth surface double layer capacitance. For example, the smooth stainless steel has 30 microfarad of double layer capacitance. This is the experimentally calculated one. Again, the double side laser arrested stainless steel gives high exchange current density as well as the roughness value. Figure E shows the electrochemical impedance spectroscopy of the as fabricated electrodes. It is clearly seen that the Nyquist loop or semicircle is high for the bare stainless steel, whereas for single it is reducing. For double side it is further reducing. So once the semicircle is reducing means it implies that charge transfer resistance is reducing, simultaneously double layer capacitance or conductivity is increasing. In addition to that, all the three Nyquist plots shows a low frequency, that is an inductive loop at the low frequency, which is highlighted by means of an red line, which is arised due to the magnetic behavior of the materials. So the bare stainless steel also has magnetic behavior, but after laser radiation, its magnetic behavior is enhanced. And figure F is for the long-term stability test, that is chronopotentiometric curves, which is recorded at a constant current of about 10 milliampere, because that is the fuel cell output current. Here, initially the over potential is decreasing up to 2.5 hours. After that, it starts to increases and attain a steady state. Why it attains a steady state before that? This zigzag motion is happening means because of the polarization. That is, the surface oxides undergoes polarization up to 2.5 hours. After that, the polarization is stopped, so it reaches the steady state. From this, we concluded that there is no correlation between the activity and stability of the electrocatalyst. And what kind of motivations we can get from this work means we need to redesign the conventional materials at micro nano scale to fully exploit its electrochemical activity through the laser texturing. So these textured material will be able to store high energy and which will be used for the future use. When we utilize this kind of laser textured material for hydrogen production, we will get enormous amount of hydrogen, and these produced molecular hydrogens will reduces the carbon footprints. And also we believe that the proposed strategy will fulfill the requirements of the hydrogen economy. And this is our eminent team. Professor M.G. SETHURAMAN, as Eli told, he is my PhD mentor. During my PhD, I thought that why we are working on corrosion, because so many various other fields are available at the time. But now I realize why we worked on corrosion, because fortunately, I can able to expand my research domains in various fields like corrosion, superhydrophobic, or tribology, or biomedical, any other things. So the basement is developed by Professor M.G. SETHURAMAN. I thank for his guidance. And Dr. Jabakumar, he is now working as a research professor in Yangnam University. He is one of the backbone for my research activities. Well-wisher too. And extend my thanks to Professor Ziong, who is the current my postdoctoral guide working in Nanjing. Such a kind human being, He encouraged a lot and he helped me a lot to stabilize this laser surface engineering works. So I extend my thanks to all my colleagues. Thank you for your active participations. Thank you, one and all.
Thank you, Karthik.
Thank you, sir.
Yeah, is there any questions from the audience on that? Okay, so it was nice hearing you again. Many people are asking for the PPT and all that. So I hope you'll be able to share after the webinar is over. Thank you once again on behalf of the Department of Chemistry. So I think I hand over again to Gautam for the next talk. Gautam, please. Mr. John?
Yes, sir.
Okay, sir, take over.
Okay. Gautam?
Yes, sir.
Okay. So the announcements, I think now it is on YouTube. Maybe you can tell, Gautam.
Yes, sir. So due to some technical issues, we cannot live with the Facebook. So please follow the YouTube link, which I have given in the chat box. You can share it to your friends, those who need the Facebook link. So you can share the YouTube link instead of the Facebook link. Okay, thank you.
Now it is
Next
Muthu
is
Prabhu's turn. Has Muthu Prabhu come online?
Yes, sir. He is online, but just 2 minutes, sir.
Okay. Oh, Muthu Prabhu is there. Good. So singer மாதிரி headphone எல்லாம் போட்டுருக்கு.
ஸ்டீரியோலாம் வச்சிருக்கிறார் போல தெரியுது.
I thought he is going to come out with some music also.
The Meenakshi madam is online. Gautam?
Just I will check, sir.
Meenakshi madam, if she is online, we will ask her to introduce Muthu Prabhu.
Okay.
So he is giving it from the department, huh?
Madam is in online, sir, but
Okay.
couldn't connect with the video.
Anyway, okay, no problem.
Just a minute, sir. I will prepare the slides for Dr. Muthu.
Probably we would have informed earlier.
We could have.
Yes.
Our Vice Chancellor in charge, Professor Sundarodilu, is there with us. We have Dr. Anita Paes, head of the department, and a host of other faculty members from the neighboring institutions. A big long list is there. So I welcome once again on behalf of the Department of Chemistry, all of you. And,
Madam is there.
Yes, I'm here. I'm holding my grandson.
Madam, can you introduce your student, madam? Is it possible?
Oh,
yes.
Of course, it's my pleasure. But anyway, you please introduce. No problem.
No, if possible, you can do it, madam. Maybe you give it to your grandson to somebody else.
Wow. He's making his felt.
Yes, you can.
Gautam, you can
display his resume.
Maybe
problem?
Yes, sir. I will share the.
Okay. We will wait.
I think you have to unmute yourself, Gautam. I mean, Prabhu, Muthu Prabhu. There is a provision to block the scratchings also. Are you able to hear us, Muthu Prabhu? Dr. Muthu Prabhu, are you able to hear me?
There is a noise from Muthu Prabhu.
Yeah. He doesn't keep quiet, makes noise, huh? You have muted your mic.
இன்ட்ரடியூஸ் பண்ணுங்கங்கறாரு. அவனை பத்தி எதுவுமே தெரியல.
இல்ல இருக்கு மேடம், இருக்கு எங்க கையில இருக்கு.
We have, don't worry. You are on. What you are speaking is you are able to hear. Is it okay?
Wait.
This is going to become the order of the day. Future, for at least for 2 years, we may not be able to have any seminars or conferences, and probably the big business of Shanghai holding the conferences will probably become a no affair from now on, and webinar is going to be part of the game. And I'm sure that there will be many more conferences by many institutions connecting people through webinar, discussing things. So one-to-one, face-to-face meeting is going to become the thing of the past, and it's all going to be through net and through web. We are going to have, and I do not know whether we'll be able to have 90 hours of teaching and all that, with UGC and ministry saying that we should have only 60 to 50, 60 hours through face-to-face and rest through online. I think with social distancing and all that, this is very convenient, whether it is COVID-19 or any other virus that is coming, to keep ourselves safe. I think this is the best of the option. Now, can we have?
Now somebody else doing something.
Yeah. They have posted.
Somebody has Syed Abdul.
Jamal Muhammad. Anyway, there should be provision for this also.
So can you see the slides, sir?
No.
Yeah, no, it is there. Yes, yeah. So it's a pleasure to introduce Dr. S. Muthu Prabhu, postdoctoral research fellow. Is Dr. Meenakshi there?
Gautam, address, there is some mistake. He is not University of Putra, Malaysia. You changed it. Yeah, okay. Copy paste. Okay.
Yeah, presently he is the, I think there is cut copy paste problem.
Madam is there?
Okay. He is presently with Alagappa University, Karaikudi. He has done his BSc.
Madam is available, I think. Madam. Madam.
No.
Yes.
எனக்கு என்ன பண்ணன்னு தெரியல. Hello.
Madam. Yes. Madam, you can go ahead.
Sir, I'm holding my grandson. You please introduce him.
Okay.
Okay.
He has done his BSc and MSc from Gandhigram Institute, deemed university. So PhD is again from the same university under the able guidance of Professor Meenakshi, and he has done his work on defluoridation of drinking water using synthetic and biopolymeric assisted materials. And after finishing his PhD, he moved over to Yonsei University, South Korea. He worked under Professor G. Lee on zero-valent ion materials for dye adsorption, and later on he moved over to Kyushu University with a prestigious JSPS award. And in fact, he has published quite a good number of articles, and his main focus of area was on the synthesis and surface modification of 2D metal organic framework and the graphene-based materials for noxious ions removal. And he was also, later on moved over to Goin Peak National University, South Korea as a research professor. And during his tenure at South Korea, he focused on photodegradation of organic molecules using MXenes. So presently he moved over to, he's a postdoc at Alagappa University. He's working as a supercapacitor using functionalized 2D materials. So he's a senior postdoctoral fellow at Alagappa University, and he has nearly 35 publications with a H index of 15. And I mean, he has filed 3 Korean patents also, a distinguished researcher, a very active researcher, I would say. I still I'm reminded of his days as a student, where he used to be a very enthusiastic student, interacting with everybody. And he has received many awards, both best oral and poster presentation awards from international conferences. He received awards like RUSA Senior PDF, JSPS, and Dr. Kothari Award. And he was selected as one among the 15 Indian researchers to participate in IGCS Winter School for Sustainable Water Management in Urban Areas, conducted by Indo-German Center for Sustainability. And he is also recognized as a potential reviewer for many journals. And his articles in the International Journal of Macromolecules is a widely cited article. And so a distinguished academician, and he used to maintain excellent relationship with all his teachers and his peer lab members. And I still remember Professor Meenakshi recalling his work even now. So that is the kind of impression he has left behind on the teacher and on the colleagues in the department. So it is a pleasure having him here. So we welcome him to India, and having joined Alagappa University, I'm sure that he'll be able to contribute much more than what he had done when he was in abroad. So thank you, Muthu Prabhu, for accepting our invitation at a very short notice. So it is your turn to deliver the lecture. So I again wholeheartedly welcome you, and then request you to continue with your lecture. Thank you. Thank you for accepting. Thank you for coming forward to deliver the lecture. You can start, Muthu Prabhu.
Yes, yes.
Muthu Prabhu?
Yes, yes, he is available.
You tell him how to avoid the scratch and all that.
Prabhu?
So audio has some problem. Prabhu is there?
No, sir, I'm searching him.
I think he is there, but I have some problem with the audio.
Name is, I think, different.
Maybe you call him over phone. What is doing? Gautam? Whether he is available or not.
No, sir. Do you have his number, sir?
I have his number. I will call him. Okay.
Okay, sir. Okay.
Hello.
நீரு அவனை அலோவ் பண்ண சொல்லுவான். நீ ஒருவேளை எல்லாரும் உள்ள
Kindly bear with me for 5 minutes.
அவனோட வாய்ஸ் கேட்கறதுல ஒரு மாதிரி இது மட்டும் தான் வருது. அந்த இதுதான் வந்தது.
We will be able to get Muthu Prabhu connected. There is some connection issue Professor John is trying to address, and we will be able to have him reconnected in another 2-3 minutes. And for the information of the participants, some of them have said that there is some problem with giving their feedback yesterday. We will try to sort out the issue, and today's feedback also will make it available so that you can fill it up and then send it to us. And one small request for the participants: please do not pester for the certificates immediately, because we have more participants and we may probably have to prepare certificates and all that. It will take some time. So probably before first week of June, we will be able to send you all the certificates. So that is one thing. And regarding the PowerPoint presentations, we are requesting all the speakers to share with them, and with their consent, we'll be able to send you once they tell us their consent. That is one of the things that I just wanted to inform you. And is he able to get? So these are all the issues that you come across in webinars. Of course, it's unavoidable. Kindly bear with us. I hope he'll be able to come. Somebody has written, thank you for telling about the certificates. I have not received yesterday something. Anyway. So Sir Guhanathan from, I think Vellore has joined us. I'm very happy to see him. So Sir Guhanathan.
Hello, sir.
Now it's okay.
Okay, thank you, sir. Sorry for the inconvenience.
Are you able to hear me?
Yeah, yes, sir. I'm here.
Okay, go ahead. It's nice having you back again, Muthu Prabhu.
Thank you, sir.
Okay, fine.
Sorry for the inconvenience.
Okay, no problem. Go ahead.
So, I would like to, yes, sir. Now I will share my screen.
Yeah.
Okay. Hope my slides are visible.
Do you know the annotation?
Yes, I know the annotation.
Okay. Then it's okay.
Okay.
Disable the attendee to annotate.
Okay. Thank you for your kind. Thank you for your kind introduction about me. Brief introduction about me. Good afternoon to everyone. Good afternoon to everyone. First, I would like to thank the organizers of this COVID-19 international webinar, especially to the conveners of program, Professor SETHURAMAN sir and Abraham John sir, and other department faculty members. Of course, they are all my teachers, and for giving me an opportunity to present my work as well as sharing my experience on this particular topic. So, okay. So now, hope my slides are visible to everyone. I'm going to introduce a new topic called mexins. Mexin is nothing but is a two-dimensional structure material. And the ene, suffix ene comes from the graphene. Since the behavior and the properties are similar to the graphene material, so the name was fixed as mexin. and which is quite new to the India. The most of the people are not aware of this material, and a few groups like in VIT and some of the IITs people are working on mixing material, and it's quite popular in US and as well as in South Korea. So I thought this mixing material will be useful to the youngsters like me. I'm also is quite new this topic, and recently we are working on it. So in these slides, I would like to focus on how the mixing materials are differ from other 2D materials, and how the material was synthesized, and what are the properties of mixing materials, and the applications towards energy as well as environment. I would like to focus on it. Before entering into the subject of mixing, I would like to explain some of the how the nanostructure materials are defined. Before my talk, there are several speakers have already explained what is nanomaterials and how the nanomaterials are useful for energy as well as environment. But I would like to briefly explain how the nanomaterials are designed, fabricated, and they're defined. The nanometers are nothing but is a particle whose size in the range of 1 to 100 nanometer, respective of dimensions considers. The couple of Ukraine scientists, Glaiter and Sprohard, have defined this. Initially, they defined fluorines is zero-dimensional, and nanotubes and nanowires are one-dimensional, and nanoflowers are two-dimensional structures. But after several years, they thought the definitions was wrong, and in 2017, the Ukraine scientist reported the modified forms of nanostructured materials. For example, if your material has all the 3 dimensions are nano-sized, then it will be a nanomaterial. The best example is quantum dots. Then, if the material has 2 dimensions are nano-sized, then it will be nanotubes. For example, the better example is nanotubes and nanowires. Then it is called as one-dimensional. Then, if the material has 1 dimension is nano-size and other than the other 2 sides, then it will be like a sheets, like a paper. Then it's called 2-dimensional structure. The best example of 2D dimensions are graphene. The known example, the popular example is graphene. And there is, if a material does not have any dimensions, then it will be a 3D structures. And the best example is carbon fluorine. Then mixing is categorized under as 2D materials. Then I would like to focus on 2D materials and the properties of 2D materials, how they synthesized from the 2D materials. Okay, 2D materials are the substance with a thickness of few nanometers or less than that of, and graphene, layer double hydroxides, metal dichalcothiones like molybdenum disulfide, and carbon nitrates and boron nitrates. These are the beautiful examples of 2D materials. And the mixing is also incorporated into the family. So we can also say that mixing is also a 2D material. And the special properties of 2D materials are high surface area and highly active sites on the edges. And it is highly disposed in all the medium like aqueous and as well as environmental medium. And it also acts as a supporting material to form the nanocomposite and nanomaterials. And also it acts as a host material to welcome in the new guest materials to make it the nanocomposites. And it can be tuned by the electronic structure by topping of some heteroatoms or the nanoparticles. And the interfacial interaction was much higher than the other materials. Also, the intrinsic activity and the atomic thickness are quite impressive than the other materials also. Basically, popularly, there are 2 methods are available to synthesize 2D materials. One is top-down approach and another one is bottom-up approach. Top-down approach is nothing but it starts with the bulk material and make it the thinner. Then the latter case starts with the atomic ingredients and assemble them together. These are the 2 methods are commonly adopted for synthesizing 2D materials. For the top-down approach, there are 2 main methods are available. One is mechanical exfoliation and another one is chemical intercalation. Mechanical exfoliation is nothing but sticky tape was applied on the surface of bulk material, then it's peel up, then it get exfoliated of a few sheets of nanomaterial. Then it converted into the nanoseeds by washing and other several as usual methods. Then in the form of chemical intercalation, the layer double hydroxide materials was introduced into the nanomaterial in between the layer, the basal planes, then it get exfoliated first, then it will easily delaminated form of nanosheet will be obtained. And for the bottom-up approach, there are two methods. One is CVD growth, and another one is molecular cell assembly. Molecular cell assembly is nothing but using the surfactant molecule to get the self-assembled layered of material. Then it will get further delaminated easily. For the CVD, it's using the vapor deposition method. Then we can easily delaminate from structures, bulk structures. From the CMI images shown in the right side of this image, this part, you can see the all the method has different structures, which is not easily described from each other. So the every method has own advantages as well as disadvantages. Okay, what is mixing? Why mixing is needed? Mixing is a 2D transitional metal carbides. It's known as mixing. It has the layered hexagonal structure, and the mixing, the suffix in emphasizes. Yes.
Sorry, the slides are not moved. Make sure the slides are moving.
Now, okay.
No.
Okay.
You just press F5. Press F5, please.
Yes, yes. Okay.
No, it is not moving.
Why my screen is fast? I don't know.
You just restart your sharing.
Okay,
Yes.
okay. My screen is not sharing well. Okay, okay. I will share again.
Okay, okay.
Okay. I will. It's okay.
Next.
Is it okay?
No, it is not moving.
Wait. Sorry for the inconvenience. Shared window is closed. Okay. Okay, I will do it again. Is it okay?
Next slide. Yeah, it's fine.
Okay.
Okay. Sorry.
Okay, sorry for the inconvenience again. Mixing is nothing but it's a 2D materials. As I already said, it has the layered hexagonal structure of metal carbides and metal nitrides. The mixing in, the suffix in to emphasize the similarity to graphene. Hence, the in is comes from the graphene material. There are more than 60 phases of mixing material was obtained. Most of them are titanium background and chromium, vanadium, and neodymium backgrounds, which exhibit properties like high chemical stability, high electrical conductivity, and environment-friendly characteristics. It has hydrophilic in nature and abundant and highly active functional groups on the surfaces. The mixing materials is similar to the an instrument called accordion. This is the portable form of piano. We can say that it easily play with the help of air. So most of the papers are coming from the title of accordion-like the images are accordion-like materials. So we can also say that the mixing is similar to the accordion instrument. So this accordion material. So this is Professor Yuri Kowarski, who discovered the new family of two-dimensional materials called mixins. He is from Ukraine scientist. He is the associate editor of ASIS Nano. Then he discovered and described a new forms of carbon called canonical and polygonal crystals. He was also named as one of the world's most influenced minds list by Thomson Reuters, Canadian Corporation Limited. Also, he has He has done conduct the hydrothermal synthesis of carbon nanotubes and show the anomalous slow movement of water in a functionalized carbon nanotubes by in situ micron electroscopy. This study ultimately lead to development of nanotubes dipped single cell probes. Okay, how the MXene material was synthesized from max phase. Okay, initially they started with many methods, but this method is mostly adopted for the synthesis of titanium based max phase. Initially they started with 3:1 1:2 ratio of elemental titanium, aluminum and graphite based material was ball milled for 48 hours. Then the powder form of this ball milled material was applied to the pressure instrument to make it a cylindrical disc with a size of 50 millimeter diameter and 10 millimeter height. Then this disc was further treated with a tube furnace for about 1730 Kelvin for 1 hour with under argon atmosphere. So the obtained maize powder was titanium aluminum carbide. And this is the raw material for MXene. This is a bulk form as shown in here the left side of image. Then this max phase was immersed in 40% HF at 313 Kelvin for 10 hours. Then we can get the final product was washed and dried and the freeze dried. Then we can get the aluminum removed pieces. The advantage of HF was to remove aluminum phase to get the exfoliated sheet. That means the bulk phase has aluminum layer. The aluminum layer to be selectively removed from the max phase to get the wide rich or the expanded structure of MXene. When the aluminum etching was removed and it was calculated, the aluminum concentration was analyzed using ICP-ES to get the quantitative amount of MXene material was obtained. Then this is the schematic representation of MXene phase was derived from the max phase. It was selectively removed, and you can see the bottom up the bottom image. The HF was selectively etched, and the introduction of new functional groups like fluoride and hydroxide on the surface of MXene, which is highly useful, which induce the hydrophilic in nature. You can see here. You can see some images of some images of max and MXene, and it was confirmed by TEM image also. Gautam, how to control again? I cannot do it here. Disable participant annotation, right?
Yeah. You just go to the top and more option.
Okay. Disable.
Attendee to annotate. Disable attendee to annotate.
Disable. Okay, I already did.
Okay.
Now, why MXene? Why not graphene? Graphene has, we know that graphene has a van der Waals interaction between the layers, which is, but in the case of MXene, which is much stronger than the graphene oxide materials, then it exhibit higher electrical capacitance, is more flexible than the graphene material and more stable, and can easily be prepared and more moldable form of MXenes than the graphene oxides compared to other form also. Then this material can work both energy as well as environmental sites. For the energy sites, this MXene material was applied to electrical energy storage devices like pseudocapacitors, lithium-ion batteries, and hybrid devices. And also, it's working for some energy obligations. And it is also focused on the flexible electronic devices. Like Samsung introduced a new graphene-based batteries. Now they are also focused for MXene materials. And on the other side of environmental application, it is focused mainly on water treatment, like absorption of toxic ions and separation of toxic chemicals using membrane technology, and the extraction of palladium group metals, especially. As you know that yesterday, Dr. Rajiv Gandhi have already explained about how the PGM material was, the palladium group metal was extracted using the calyx arene materials. We are also focused, myself also focused on the extraction of palladium group metals using mixin-based material with the substituent of sulfur materials to the functionalization. Then also we have focused on photodegradation studies of toxic molecules and also capacitive deionization also. So in the form of composite materials, it highly conductive and the high strength and low permeability polymers, and it has high toughness ceramic-based metal composites. For the energy application, I would like to focus on energy of first. Supercapacitors are nothing but it store and release energy by reversible adsorption desorption mechanism of ions at the interface between the electrode materials and the electrolytes. Until now, there are a lot of 2D materials was focused for the supercapacitor application, especially for molybdenum disulfide, vanadium disulfide, LDH, the sulfur-doped LDH materials, and the metal organic frameworks and graphene-based materials, carbon nitrides, and recently added mixin materials. This among the materials, mixin materials showed exhibited a higher lower contact resistance, higher capacitance, and a better and also showed excellent cyclic stability with 100% capacitance retention even after 1000 cycles of at the scan rate 50 millivolt per second. Then initially, group of people from China have developed supercapacitor application using mixin-based materials. They intentionally developed porous materials and the porous and the material mixin phase. They found that it is the best one. They showed the specific capacitance is more than 355 farad per gram with a scan rate of 10 millivolt per second with the help of 3 molar sulfuric acid as a electrolyte solution. The mechanism mainly follows for pseudocapacitance. If we use the neutral electrolyte, then it will form the EDCL mechanism also, which was also then the graphene-based materials. A group of people from China, they developed a graphene material which was compared with the mixin materials also. They initially they took the graphene sheet and heated with different temperature from 200 to 900. They found that up to 200 degrees Celsius, they achieved more specific capacitance with the help of 3 molar KOH electrolyte. But when compared to the mixin materials, is found to be lesser. And this is the simplest example I'm telling here. And also the mixin-based material with the PVA, which showed the higher volumetric capacitance, which is 2 times higher volumetric capacitance than the graphene-based material with the help of 1 molar potassium hydroxide as electrolyte. From the report of science, we have the titanium-based mixin paper demonstrated excellent cyclability to store 300 to 400 Faraday per gram with a translated 3 to 4 times much higher energy than the commercial activated carbon as well as graphene-based materials developed for capacitor applications. Not only in the capacitor application, and I would like to explain a simple method to incorporate some nanoparticle onto the mixin. Recently, there is a group from India who is working in South Korea who developed manganese oxide nanoviscous and mixin material. The appropriate amount of mixin was added with manganese sulfate solution. Then the manganese sulfate solution was oxidized with the potassium permanganate. Then most of the manganese oxide was coated, intercalated into the basal plane of the mixin, which was confirmed by XRD as well as TEM image. The TEM image, you can see the carbon, manganese, and oxygen are similar patterns, or showed the similar patterns than the titanium, which means that manganese does not form any. The manganese does not form any bonds with the titanium. Instead, it forms with cation pi interaction with carbon materials. Also, it has shown the specific capacitance of more than 200 Faraday per gram, which is 3 times higher than the pristine forms of mixin, which also showed the more than 88% of cycling stability of even after 10,000 cycles. Also, this material is also compared with the graphene-based material, the manganese oxide with the graphene-based material. Then it showed lesser specific capacitance than the mixin-based material. So we are also starting some works on supercapacitor application after joining to the Alagappa University. The mixing material was given by my professor Park from Kunpuk National University, South Korea. We have also started with some bimetal oxide and selenium dope, co-doped and mixing. We showed the specific capacitance of 600, almost 700 Faraday per gram with 1 molar KO solution. See, we are at the starting stage, so we are also waiting for some spectrophotometric evidences as well as spectrochemical evidences to publish this paper also. Then not only in the supercapacitor application, they are also focused. A few groups in South Korea have also focused on sensor applications, where they have taken a titanium backbone of mixin for volatile organic compound gas sensing. Initially, the highly electron donor moiety of acetone, ethanol, methanol, and ammonia have taken for this study. They have observed on the mixin moiety. The mixin moiety has the functional groups of hydroxide and oxide on the edges as well as basal planes of mixin, which tend to form hydrogen bonding. And among these, ammonia has higher sensing responses due to large absorption energy, which was confirmed by TFT studies also. Then the absorption energy of ammonia is stronger than the other molecules, such as methane, carbon monoxide, carbon dioxide, and nitrogen dioxides at room temperature. Besides, there are a lot of applications are focused for lithium-ion batteries, fuel cell application, and proton up conversion reactions using mixin-based materials. I have not shown, I have limited time, so I have shown only the 2 applications of energy. Then I would like to move on to the environmental applications. Since the hydrophilic surface is more beneficial for always the absorption of polar ions and the ionic species, any ionic species, the most of the termination of mixin has hydroxide oxygen functionality, which will helpful for absorption of toxic ions as well as complex with the toxic cations also. Initially, the uric Ogasaki group, with the help of Ogasaki group, they have started with introduction of sodium ions into the basal plane of this mixin. Then it forms a sodium form of alkylation form of mixin for utilized for lead ion removal. They confirmed that the sodium ion was intercalate rather than the formation of upper layer. This surface adsorption, it was intercalated between the layers, was confirmed by PXRD studies. You can see here there is a piston form of max space. Then the D space of 002 has been shifted towards the lower angle of 2 theta, which confirms that the structure has delaminated, which means that sodium ion has incorporated between the layers. Sodium ion has incorporated between the layers, so the seeds are get exfoliated. Also, further, with the help of hydrogen fluoride. Then this material was absorbed for lead ion with the initial concentration of 20 ppm. With the initial concentration of, I didn't show that, the initial concentration of 50 ppm. Then it showed that the absorption was cation exchange mechanism as well as complexation. Then the material was again regenerated using the suitable eluent like nitric acid. Then you will get the original form of mixin. Then we can get again with the sodium to incorporate sodium. Then you will get the original form. Then we can utilize further. This, when we found that the absorption capacity was much higher, that means 140 milligram per gram using this sodium form of mixin, then which was compared with some graphene-based materials, then it shows lesser amount, like 36 milligram per gram with graphene-based materials, which is almost 4 times lower absorption capacity of graphene oxide than the mixin-based materials. This is the quite advantages of mixin-based material. Then also one of my friends in Kunpuk National University have started work on molybdenum disulfide with mixin nanocomposite to absorb mercury ions from the solution. He started with this is the simplest form of 2D interaction. The metal sulfides, the molybdenum sulfide has a 2D structure, and the mexine has also 2D, and the 2D interaction was happened. Then the sheets are arranged in a sandwich-like structures. The mexine molecule are just dislocated for several levels. Then you will get slightly a delaminated structure, which was utilized for which was applied for the development of molybdenum sulfide on the surface of mexine by a hydrothermal method. Then we confirmed that the molybdenum sulfide was intercalated between the layers rather than on the deposition of the mexine phase by XRD results. Then the mechanism was explained well using the mercury was absorbed on the mexine phase through electrostatic interaction, ligand exchange, complexation, as well as soft to acid, soft base interaction. Where since this molybdenum sulfide has a sulfur moiety which has soft acid, then the soft base of mercury will interact easily. Then the soft acid, soft base interaction was happen with the help of HSAP principle. Then we can see the some images. We can see you can see the crystalline form of mixin. Then after coating with the molybdenum sulfide has both the layers above and as well as the basal plane, the interlayer surface. I have also started some work on copper adsorption. We have also started some copper adsorption studies with the help of mixing materials, which showed the higher adsorption capacity. Initially we have started with the sulfur doped graphene material towards the copper adsorption, since sulfur is a soft moiety which can easily absorb by copper by as well as we know the well-known HSAP principle. The sulfur doped graphene material has shown lowest adsorption capacity compared with the other forms. When compared with sulfur doped graphene oxide, mixing showed little, almost 0.8 times higher than that of sulfur doped graphene oxide. Then we have optimized the concentration from sulfur doped graphene oxide from 5 to 50%. Then we get the almost 2 times high, almost 2.5 times higher adsorption capacity than the raw forms. Then we have taken initial amount of 10 milligram per liter with a pH of 4.8. We have also checked the mechanism. Then the mechanism was complexation, electrostatic interaction, ligand exchange mechanism. We are also waiting for some more evidences to explore the particular mechanism and it to be published. Then this was the first study using the mixing based materials, and of course this paper will be soon published. This we have started with arsenic, since these ions like hydroxide and oxide on the surface of a mixing material will be more helpful for adsorption of arsenite and arsenate. We have started with different lanthanum and zirconium forms of composite forms of mixing. We have purchased commercially lanthanum hydroxide and zirconium oxide, which was intercalated on the mixing phase. Then it showed lesser adsorption capacity compared with other forms. Then also the another form of lanthanum zirconium, which was synthesized by simple one-step one-part method on mixing moiety, which showed the higher adsorption capacity than the commercial phase. Also, we have developed already the lanthanum fumaric MOF moiety. From the MOF, we have developed lanthanum oxides, that means LOXX. Then we combined with zirconia moiety, then we intercalated on the mixing phase. Then we showed higher efficiency than the reported material for lanthanum based materials until now. Also, the interesting phenomena was that the lanthanum zirconia based material was showed almost 80 milligram per gram of adsorption capacity than the arsenate phase due to the pH of the solution, where the arsenate has the pH is 6.2, which is highly the arsenic was in the +5 oxidation state, whereas the oxidation state of arsenite is 3 at pH 8.7. Until now, there was 0 oxidation state, so hence the arsenite is more highly toxic than the arsenite species. Then we found that arsenic by the metal ratio, which was 2, we confirmed that each metal can absorb 2 arsenic ions. That means each ion, lanthanum can absorb one arsenic as well as zirconium can also absorb, as well as both lanthanum, oxygen, zirconia can form bond, lanthanum, oxygen, zirconia, which can absorb arsenic by bidentate complex rather than the monodentate complex. This is the most the valuable one for the absorption studies. Then the mechanism was complexation, electrostatic interaction, and as well as the Lehigh exchange. Then when I was in South Korea, the one of my juniors, Vigneshwaran, came to South Korea for his internship program. Then we have started some bimetal sulfides. There are also 2D materials which was intercalated on the mixing material for bisphenol degradation, where we have successfully attempted and we have successfully got results for the intercalation of mixing materials into the mixing materials. By we have synthesized nickel, magnesium layer double hydroxide, which was further treated with some sulfur moiety to get sulfur form of mixate, which this is the more beneficial. Sulfur is more beneficial to degrade another material due to the electronegativity also. Then this material was combined with the help of some surfactant. Then we found that this material is highly effective to degrade the bisphenol A. This was confirmed by the ESR results. Then this paper was accepted. This is the main mechanism behind how the bisphenol A also degraded. We have also tried to degrade and rhodamine B as well as phenol degradation. Both are working well on mixing based material, rather which was compared with the graphene based material, but it is higher efficiency and the lower rate of adsorption capacity, lower rate than the other 2D materials also. Then another work, another similar work was done here in Alapa University. We have started copper lanthanum sulfide and mixing for bisphenol A degradation. We found that these particular bimetal oxides are intercalated, confirmed by PXRD studies, when the space value was increased drastically from the 9.9 to 14.2. This material, the mixing material was totally delaminated. Then we found that good results using sonocatalytic degradation. Sonocatalytic degradation is nothing but sonication along with visible light. Then the photo, we have also checked the photo degradation, sonocatalytic degradation, photolysis with photocatalyst and sonolysis. Among them, sonocatalytic degradation was much higher efficiency than the other methods developed here. We are also looking for the better results on the mechanism part. Then we found that it was quite impressive results we got. Then recently there was one group from India who is working in abroad. They have also tested towards the carbon dioxide reduction using mixing based material. They developed some metal oxide, bimetal oxide on the mixing phase. They successfully incorporated to delaminate the mixing sheet to get the nano sheets. They have tested with towards the carbon dioxide reduction. It found from the cyclic voltammetry, it found that they got the current density of 18.745, which is much higher than the other materials developed for this study. Then they have utilized carbon saturated solution in 0.5 molar sodium hydroxides. Besides, there are a lot of approaches like environmental approaches like membranes and desalination applications, as well as capacitive deionization was also approached, and they found that mixing materials will be more popular in the coming 40 years. And to conclude, these super properties of mixing seeds makes them promising candidate than the other alternative materials like which will be the alternate material to the graphene and other 2D materials. Compared to the intensive studies on graphene, the investigation of mixins are still in embryonic stage. We are also working on the embryonic stage of supercapacitors as well as for the towards the water treatment studies. Also, when we applied by heat treatment, it's an effective way to eliminate the surface functional groups of mixins. And we can also tune by the Trellman treatment to get the more functionalities. As well as we can also functionalize some functional groups through the chemical bonding as well as van der Waals interaction to effective utilization of energy as well as environment. Then I would like to thank my supervisor who built me what I am now, Professor Meenakshi, and the other staff members. Of course, they played a key role they are all my teachers and the other who developed me, and the organizers of this webinar particularly. I would like to thank them. Then I would like to thank Professor Lee, Yonsei University, Professor Sasaki, my JSP's mentor, QC University, as well as Dr. Park from KNU. Then I would like to thank the Pardimal Kalayan, Department of Industrial Chemistry, Alapa University, Karaikudi, as well as other department faculties in Alapa University. And the funding agency, I would like to thank, especially thank the funding agency like RUSA, JSPS, NRF, KRF, UGC, as well as DST, and my co-workers and my master students here. And thank you for your kind attention, and stay safe and stay alive. If you have any question, kindly let me know. I will be happy to answer you, and as well as you can also type your question in the chat box. Then I will with your email ID so that I can answer you by email.
Thank you, Muthu Prabhu.
Thank you, sir.
Gautam?
Yes, sir.
So we have time for 2 or 3 questions, and then
sure.
we will wind up.
Sure, sir.
Okay.
Anybody want to ask question? Please raise your hands.
Or put it in the chat box.
Yes, Dr. Ruchi Dubey. Dr.
Hello,
Ruchi
good
Dubey.
afternoon. Good afternoon.
Yes.
This is Dr. Ruchi. I want to ask Professor Muthu Prabhu, is it possible to use these devices as a reusable devices? Maxine.
Sir, I couldn't hear voice. I couldn't hear your voice.
Please repeat again.
Can Maxine be used as reusable devices? Like we are absorbing something on it, then afterward, by the absorption, can it be removed some harmful substances from it?
Gautam, can you help me?
Can the Maxine is the reusable device for absorption studies?
Yeah, of course. We are also using for arsenic studies. We have utilized the arsenic removal.
Can you use it again and again?
Yeah, of course. Of course, we can use it again and again, so many times. Since when we compared with graphene oxide after prolonged using of graphene oxide, then get aggregation.
How will you regenerate?
Say using sulfuric acid or nitric acid, depending upon their pollutant.
You can regenerate.
It can be regenerated.
Okay.
The main advantage of this material is when you use graphene oxide, it get aggregated after prolonged using for regeneration study. But in the case of Maxine, it has already the titanium in the phase, so it will not get easily accumulate.
Okay.
Won't it add to the metal toxicity?
So metal toxicity is aluminum. So if you using max phase directly, then aluminum will be leached out when you use HF. Then, but the toxicity is quite less compared to other LDH materials and MOF materials.
Good, sir.
Okay. Maybe we have one more question.
Of course.
Mr. Manimaran, Dr. Manimaran. Manimaran.
Manimaran is not there. Huh?
Yes. Saranya Sri.
Okay. Saranya Sri.
Saranya Sri from GRIT Hyderabad.
Please go ahead, madam. Saranya Sri. Okay, Gautam, we will wind up. Okay. Concluding remarks by Professor MGS.
It's a duty to thank every one of you for participating in this international webinar. First, I should thank the Vice Chancellor in charge, Professor Sundaravadi, for giving the go-ahead signal. And I should thank the registrar for permitting us to go ahead with this webinar. It is my pleasant duty to thank my head of the department, Professor Anita Payas, and all my colleagues, Dr. Meenakshi, Dr. Yelango, then Dr. Ramesh, Dr. Satish Kumar, Dr. Kali Muthu, Dr. Srinivas Perumal, Dr. Arunachalam, Dr. Vijay Vadanad, and Dr. Sivaraman, everybody. Of course, my partner in this webinar organization is Professor Abraham John, and he stood by my side, and in fact, he left no stone unturned for making it very successful. And for all his efforts, I salute you, sir, and I thank all my colleagues, the authorities of GRI, and Dr. Gautam, who was really toiling for over 3 to 4 days. And I thank all the speakers, Dr. Balakumar, Dr. Rajiv Gandhi, Dr. Kali Muthu, Dr. Gautam, Dr. Karthik, and Dr. Muthu Prabhu for their wonderful presentations. Though there were some issues regarding connectivity and all that, but they tried their level best, cooperated with us, and came out to the best possible things. So I'm indeed thankful to each one of them, and I'm thankful to everybody for making it a good success and getting about 500 nearly participants, and with YouTube participants probably it may run into thousands, but still we could reach only through this Skype. So the technology inventors also should be thanked for this enabling mechanism they have devised, so which has enabled GRI to reach out to so many. And I'm very happy to say that this department always with the NMR facility, with SEM facility, and with LCMS facility helps everybody. And whoever wants to avail these, there are the informations are posted in the Gandhigram Rural Institute website. So probably we'll be able to help you also. And I think it is certain that Gandhigram will become the destination for serious researchers, as you are able to see 6 scholars who have come out of the portals of these institutions doing very well. And there are many more. Probably if we have to organize webinars on by our postdoc students and others, we may have to organize several such webinars, because the list of students who have completed their PhD and who are settled in abroad, who are working in various universities as postdocs and faculty members, the list is long. So to that extent, this university has groomed the scholars, and I think we should we should congratulate the efforts of everybody for making it this webinar a successful one. So I thank you all. I thank once again Professor John. So one final word from John before we conclude. So over to Professor John. John, sir. Hello. Professor John, are you there?
Sir is not in online, sir.
Not in online, huh? Yes, anyway, so I thank Dr. Gautam once again. So thank.
Sir is online, sir.
Online, huh? Okay. If he's there, call him. Okay. One final word from John, sir.
So once again, I thank Professor SETHURAMAN for his concluding remarks, and also I thank all the participants for their patient listening. Of course, as he said, we have some technical issues. Maybe hope that will be rectified in next our forthcoming webinars. We are also planning for next webinar. We will be announcing soon. And those who need that e-certificate, they have to submit their feedback forms. I think Gautam, today itself,
Yes,
yeah.
They have to complete their today you have to, and please patiently wait for 10 days, because we have so many participants. We have to prepare it. We will send to everybody. I am very sure that we will send each one of you, but please be patiently wait for 10 days. We'll send it after 10 days. Okay. Thank you very much. See you once again.
Thank you.
Another webinar. Thank you.
Thank you, sir.
Thank you, sir. Thank you.
Thank you for that.
Okay. Bye.
Bye.
Okay. Thank you.